Today, we're going to talk about something that just sounds impossible: bendable concrete. The official name is Engineered Cementitious Composites, or ECC. And really, it's a complete rethink of the most common building material on the planet. For those of you deep in your material science or civil engineering grad programs, this story is a perfect case study in how questioning one simple assumption can change everything.
Think about concrete. The first words that come to mind are probably strong, rigid, solid. But here's the twist. Its greatest strength, that rigidity, is also its biggest weakness. It's a fatal flaw. So the whole innovation here kicked off with a really simple, almost childlike question. What if it didn't have to be brittle? Just asking that one question challenges a way of thinking that's been baked in for over 200 years. So what are we actually talking about here? Well, on one hand, you've got regular old concrete. It's brittle. When it fails big. You get one huge crack, water seeps in, the steel inside rusts, and boom, you've got a massive repair bill. But ECC, it's a completely different animal. Under the same stress, it doesn't just snap, it bends. It develops this whole network of thousands of tiny, harmless cracks that spread out the energy and actually make it stronger. The result is a material that's just unbelievably durable. And we're not talking about a small problem. I mean, concrete is everywhere. It's the literal foundation of our world, our roads, our bridges, our homes. Professor Victor Lee, the guy who invented ECC, argues that this single property, its brittleness, is the real reason our infrastructure is crumbling and why we have to spend so much energy and create so much pollution constantly making new cement to fix it. And this isn't some abstract academic debate. Look at this number, 56,007. That's how many bridges just in the United States are considered structurally deficient. It's a huge, constant crisis. It's a daily risk and a bottomless pit for public money, all because the material we depend on has this built-in flaw. So how do you even begin to solve a 200-year-old problem? This is where the story gets really good. It becomes about Professor Victor Lie and his quest, a quest that a lot of his colleagues thought was, well, kind of nuts. For any of you just starting your own research journey, I bet that sounds a little familiar. And you don't have to take my word for it. Here it is, from the man himself. I mean, can you imagine being a young assistant professor and you've got senior experts in your field telling you that your main research idea is foolishness? They basically told him that cracks in concrete were a law of nature, something you just had to accept. It's such a powerful reminder that the biggest, most disruptive ideas often start out looking like crazy ones. You know, when all the established wisdom tells you something's impossible, you're not going to find the answer in the current textbooks. You've got to look somewhere else. For Professor Lee, that somewhere else was the natural world, which had already solved this exact problem millions of years ago. He looked at nacre, mother of pearl. It's made of about 95% aragonite, which is basically just brittle chalk. But the way nature arranges that chalk on a microscopic level makes the final material incredibly tough and ductile. And that was the light bulb moment. If nature could build something strong and flexible out of brittle parts, why couldn't we? That idea, that conviction, was what powered this whole thing forward. Okay, so having a great idea inspired by a seashell is one thing. Actually engineering it is something else entirely. The key was to stop thinking about concrete like a simple recipe you just mix up. The new approach was to design it intentionally, starting from the tiniest scale and working your way up. It's a design philosophy called micromechanics. Micromechanics is the whole scientific backbone of ECC. It's all about understanding exactly how the tiny little pieces, the individual fibers and the cement paste around them, behave together. If you can control those interactions at the micro level, you can actually dictate how the final material is going to behave on the macro level. In this case, you can design it to be ductile. So the whole process really breaks down into these 3 tailoring steps. First, you tailor the fibers themselves, picking special polymer fibers that are designed to bridge over cracks. Second, and this is the genius part, you tailor the interface. That's the bond between the fiber and the cement. It can't be too strong or the fiber will snap. It can't be too weak or it'll just pull out. It has to be just right, so the fibers can slip and stretch. And finally, you tailor the cement mix itself so that it all works together in perfect harmony. Okay, so the science is absolutely fascinating. But for anyone who's spent months on a research project, you know the real question is, does it actually work in the real world? So let's look at the results. And the answer is a huge, resounding yes. When you push this material to the absolute limit, the cracks that form are less than 1/10 of a millimeter wide. That is literally finer than a human hair. So instead of one massive catastrophic fracture, you get this huge distributed network of thousands of tiny microcracks. They're basically invisible, and more importantly, they're structurally harmless.
So why is it such a big deal to keep these cracks so tiny? Well, that's the whole secret to durability. Because the cracks are so small, it's incredibly hard for water, road salts, or anything else corrosive to get inside. This protects the steel rebar from rusting and expanding, which, by the way, is the #1 killer of traditional reinforced concrete. The end result is a structure that can last for decades longer, with way less maintenance.
And this is not just some cool material that lives in a lab. ECC is out there, being used in some of the most demanding projects you can imagine. We're talking about seismic dampers in skyscrapers in earthquake-prone Japan, seamless bridge decks that get rid of those awful failing expansion joints, reinforcing high-speed rail lines, and repairing critical infrastructure like dams.
But what's really, truly exciting is that making concrete bendable, that's just the beginning. ECC is turning out to be a platform for creating a whole new generation of smart, multifunctional materials for our infrastructure. And this is where it really starts to sound like science fiction. We are talking about self-healing concrete, where water actually helps it seal its own microcracks. Or self-sensing concrete that can tell us when it's being stressed or damaged. Even materials that can adapt to temperature to make buildings more efficient. Or surfaces that can literally help clean pollution from the air. This is the research frontier, and this is where a lot of you could make your mark. And that really brings us to the final, most important point. This was never just about building better bridges. Professor Lee connects his work directly to the biggest challenge we all face. Building infrastructure that is more durable, more resilient, and more sustainable isn't just a nice idea anymore. It's a necessity. This quote is a powerful call to action for the next generation of researchers. For you, the work you're doing right now, the foolish ideas that you're pursuing, they just might be the ones that make all the difference.